SwayamPrabha. Digital India. Educated India.
Hello everyone. So in the last class, we started to discuss the so-called random nature of turbulence. We looked at some repetitions of turbulent flow experiment recordings and saw the random behavior. And we illustrated that random behavior by looking at a much simpler system and saw how even the slightest change in initial conditions would almost lead to a chaotic behavior of the system, meaning a chaotic change in behavior of the system. So obviously the Navier-Stokes equations or a turbulent flow behavior would be much more chaotic, in the sense its response to that change in initial conditions would be much more obvious and would be much more fluctuating. So that took us to the point where that we started to characterize random variables. So if the fluid flow is exhibiting a seemingly random behavior, then predicting U exactly might be difficult. So on the other hand, can we start to predict maybe the probability of, say for example, velocity being less than 10? This just as an example. So the probability of an event can be predicted probably better in a slightly easier way, rather than predicting the exact value, because the system is behaving in a random manner. So here what we are now doing is, if you look at the figure here on the slide, it is a sketch of the sample space showing the probability of events. The first one, A, is showing what is the probability of, say for example, velocity being less than a particular value VB. What is the probability? So the probability, the B is a region showing the values of velocity less than VB. And C here in B, it is showing the region for values between VA and VB. So now the question is, what is the probability of B and what is the probability of C? So B and C are events, okay? B and C are events, and now the question is, what is the probability of B and what is the probability of C? Probability of B is the probability that velocity stays below VB, and probability of C is the probability that velocity stays between VA and VB. That's the question. So what we are trying to do is, we are trying to predict the probability of events rather than the value itself, value exactly. So here again, we start to define what is called a cumulative distribution function, a CDF. CDF is the probability of an event C, where you have the probability of velocity being between VA and VB. So if you define capital F of V as probability of U being less than V, okay, so I want to make some notations clear here. Capital F is used for CDF, the cumulative distribution function. P is obviously probability, U is your actual variable value, and V is your sample space. What do I mean by that? What do I mean by sample space? Meaning all possible values that you can take. Okay, all possible values that you can take. So for example, if I have a jet flow where water is coming in through the nozzle at 10 meters per second, most likely I am not going to have a sample space that extends to 1 million meters per second. This is an exaggerated example, however, that still holds. My velocities should stay typically, say, within 10 to 50 meters per second at the most, highest value. It could be maybe 100, maybe 200, but definitely not a million or 1,000 even. So your sample space determines what are all possible values that it can take. That's your sample space. Again, capital F is your cumulative distribution function. P is your probability, how you represent probability. U is your velocity value or variable value in this case, because we have not gotten to velocity yet, but we are getting there, isn't it? All of this is a preview to how we would describe velocity. So we might as well call U is like your velocity. However, we are only considering a single component. We will move to multiple components later. Let's try to understand the concept first. And V is your sample space. The probability of an event C is the probability that U stays between VA and VB. Now, if I do the CDF, cumulative distribution function, the cumulative distribution function is P being between VA and VB. So if it is the probability that U is between VA and VB, or P is the probability of U less than VB minus probability of U less than VA, or the cumulative distribution function of VB minus the cumulative distribution function of VA, isn't it? That is this range here. That is what is shown here. If VA and VB are these two values, then the probability that velocity stays between VA and VB is this value here. That is your probability that the value stays between VA and VB. Now, if you look at the CDF is always going to be an increasing function, and we'll describe that as well. What is shown here in the second figure, in figure B, is the probability distribution function, not the cumulative distribution function, the probability distribution function, which also we'll describe. For now, just consider that it is the derivative of the function above. The probability distribution function, PDF, is the derivative of the CDF. So, three basic properties of the CDF. Okay, let's start with the CDF, is that f of minus infinity is 0. Why? Because you cannot have a value less than minus infinity. That's the lowest value possible. So probability of u less than minus infinity is impossible. So f of minus infinity is 0. F of infinity is 1 because all values are always going to be less than infinity. So probability of u less than infinity is a certainty. It's certain. So now, if you consider that it goes from 0 to 1, it has to be an increasing function, and f of VB is always going to be greater than f of VA, since VB is greater than VA. So that means the CDF is always increasing. I hope that is clear. So the CDF is always increasing, as seen by this figure where it is continuously increasing. It eventually goes to 1, it starts from 0, and all CDFs are like this. It starts from 0, it increases and goes to 1. And it is always increasing. Now the PDF, the probability density function, is defined as the derivative of the CDF. So ddv of FV. And because the CDF is an increasing function, the PDF is always going to be non-negative, isn't it? It is always going to be positive, as is indicated by this one. It's positive, always. That is because the CDF is an increasing function. So you take a derivative of that, it's always going to be positive. It's never going to be negative. That's what we mean by that. Now, the PDF is non-negative, so that's one property. Since the CDF is always starting from 0, and always ending up at 1, those are constant values, the f of minus infinity and f of infinity are going to be 0. So it always starts from 0, ends at 0. That is what you are seeing here as well. It always starts from 0, ends at 0. In addition, there's one other rule for the PDF. The fact that it satisfies the normalization condition. So minus infinity to infinity FV dV you take the sum of all probabilities, isn't it? You take the sum of all probability density functions, it will come out to 1. That's because all the probabilities have to add up to 1, isn't it? So if you take an integral of your PDF, it's basically the sum of all CDFs, which comes out to be 1, because your CDF ends up at 1, right? Your CDF ends up at 1. Remember, you are taking, when you take the integral of the PDF, the differential of the CDF is the PDF. So when you take the integral of the PDF, what you're getting is the sum of all CDFs. If you're taking the sum of all CDF, the sum of all probabilities, so the sum of all the probability of all the events, which has to be 1. So the normalization condition satisfies as well. So here, so that essentially, in other words, the probability is the integral of the PDF, and that is why it comes out to be 1. So this PDF fully characterizes a random variable. Okay, this PDF fully characterizes because it predicts the probability of every event happening with respect to the velocity. Now, if you have 2 or more random variables that have the same PDF, they are said to be identically distributed or equivalently statistically identical. If you have two or more random variables that have the same PDF, and that is what we mean by PDF fully characterizes the random variable. Now, from PDFs, you can calculate statistics. The basic statistic you can calculate is the mean or the average, and what we call in statistics as expectation of a function of a random variable. So U bar, the angle bracket, is what I'm using to represent a mean. So the U bar or U mean is minus infinity to infinity V times FV dV. So V is your sample space variable. So you're integrating the product of V times its PDF over the entire range, and that is your mean. The fluctuation from the mean is given by small u is capital U minus U mean. So the variance is sigma U squared, where sigma U, remember, is the RMS. This is the var of U, which is basically variance of U, is also represented like this. U squared mean is, so if I take U, it is U minus U mean, isn't it? Small u is capital U minus U mean. So U squared, since you are taking it in the integral, it has to be in terms of the sample space variable. So it is V minus U mean squared times FV dV, going from minus infinity to infinity. So that is your second central moment. Your variance is your second central moment. Similarly, you can take your nth central moment, and let's call that mu n, mu subscript n is U to the power of n mean. U squared mean is your variance. U to the power of n mean is your nth central moment, is V minus U mean. This whole thing to the power of n times FV dV. All of them are integrated with the PDF by multiplying it with the PDF. Keep in mind, this is your nth central moment. So your mu 0 is 1, your mu 1 is 0, and your mu 2 is your variance, sigma U squared, which is what this is, right? This is your mu 2. Mu 0 is obviously 1 because your 0th central moment is 1. Your first central moment is 0. It is not your mean, it is 0. Because if you substitute, mu 1 becomes minus infinity to infinity U minus U, isn't it? FV dV. Obviously this comes out to be 0 because it is 1. You understand? Now, the standardized random variable Okay, this is just a way of representing a normalized value. We call it standardized random variable u hat. We are representing it by u hat. Corresponding to u is u minus u mean divided by sigma u. So we are normalizing it using the mean and the RMS. And then standardized PDF is f of v hat is sigma u times f of u mean plus sigma u v hat. So that's the standardized random variable. So you can go forward and then find out standardized moments of u. So mu n hat is un mean divided by sigma u to the n, or mu n divided by sigma u to the n, because the numerator is the same as mu n. And then this you can write it as vn fv, again all hat variables indicating that they are standardized values. So remember, the 0th standardized moment is 1, the first standardized moment is 0, just like previously, and since you have normalized it, the second standardized moment now is 1 again, and this third standardized moment is what we call skewness, and the fourth standardized moment is the kurtosis in statistics. You can define a characterization function for the random variable as psi s, which is e to the ius, which is minus infinity to infinity fv to the ivs. This is a characterization function for a random variable. This integral we will see later is used to calculate the inverse Fourier transform, and psi of s and fv form a Fourier transform pair. We'll see all that later. But these are ways to calculate statistics. Now, with that, let's look at some examples of PDFs. So we characterize random variables. Let's look at some examples of random variables. So an example of a random variable, a standard one, is a uniform random variable. What does it do? So the PDF mathematically is defined as 1 over b minus a for when v is between a and b, and it is 0 for v is less than a and when v is greater than b. So as you can see, it is easier to look at probability first. It is 0 here, and from a to b it continuously increases and becomes 1 here. This value is 1. This is 0. So since a CDF always is increasing and it goes from 0 to 1. So it is between a and b. Now if you look at the PDF only exists between a and b. Everywhere else it is just 0. So here the value cannot exist, and here also value cannot exist. It only exists in this region between a and b. So it can only hold values between a and b. And that value is 1 over b minus a. That's the PDF. This is a uniform random variable, meaning it has a constant value, PDF. It has a constant value between a and b. And that's why we say it is a uniform random variable. Now, if I take an exponentially distributed random variable, this is again very different. Here, it is 1 over lambda exponential minus v over lambda for v is greater than or equal to, lambda, and for v is less than lambda, it is 0. So here, what I have is, I have something that goes like this, again from 0 to 1. And here what I'll have is, if I look at the PDF, if I take a derivative of that, it is exponentially decreasing. So this would be v is greater than or equal to 0, and this would be v is less than or equal to infinity. So what I have is, it actually asymptotically goes to 0. Then I can look at a standard Gaussian random variable. So Gaussian function is something you would have heard before, the so-called bell curve for the PDF, and that's what you see. This is a bell curve. The normal or Gaussian distribution with a mean mu and a standard deviation is given by this equation. This is the PDF for that. What is shown here on the top is a CDF going from 0 to 1, whereas this is the PDF shown below. Now, if u is normally distributed according to the above equation, and you take a standardized equation. So u hat is u minus mu divided by sigma. So standardized Gaussian random variable. Then as you can see, you can get rid of the mu and sigma from the equation, and your standardized PDF looks like this: 1 over square root of 2 pi exponential minus half v squared. What is shown here is a standardized Gaussian variable. So this has a mu of 0 because you have standardized it. It has a mu of 0 and a sigma of slightly close to 3. That's what happens. Next one is a log normal random variable. A log norm, again, another kind of, this is used a lot in combustion calculations as well for describing mixture fractions. So the log normal random variable is described by this equation: 1 over y sigma square root of 2 pi exponential minus half natural log of y minus mu the whole square divided by sigma squared. So here, as you can see, the CDF and the PDF are given here for the log normal. This is the for different values of the variance of y, okay, for the mean, where the mean is 1 but variance of y is given by values of 1 over 20, half and 5. So this is a log normal random variable. Another example. Here we are showing a gamma distribution. So if you have u, which is a random variable with mean u and a variance sigma squared, then the PDF of the gamma distribution is given by this. So here this equation, you have 1 over the gamma function of alpha times alpha over mu to the alpha times v to the alpha minus 1 exponential minus alpha v over v. So this is again another example of a random variable, and this is a CDF and a PDF shown here. Now let's say you have a random variable that takes a value of a. I'm showing another example here that takes a value of a with a probability p and a value b which is greater than a with a probability 1 minus p. Okay, so it can only take two values, a and b. Obviously, if one of them it takes it with a probability of p, other one it will take it with a value of with a probability of 1 minus p. So we represent the CDF like this: f of v is equal to 0 because you cannot take any value less than or equal to a. And for a and b, for between a and b, it has a probability of p, and for greater than b, it has 1. So if you take the CDF to write it as a single equation, we write it as p times, we use the Heaviside function, because as you can see, it's a discrete probability. It's a discrete probability. It has a probability of p between a and b, and above b it has 1 because it takes two discrete values. So we use the Heaviside function to write it as a single function. So f of v is equal to p times the Heaviside function of v minus a plus 1 minus p Heaviside function of v minus b. So what happens is, as is shown in this figure, it takes between a and b it has a value of p, and above b it has a value of 1. So less than a it has a value of 0, meaning it has a probability is 0. But between a and b the probability is p, and above b the probability is 1. So you can see this discrete probability by two delta functions here, because the derivative of a Heaviside function is a delta function. We wrote the CDF as a Heaviside function. So p times h v minus a and 1 minus p times h v minus b, isn't it? P times h v minus a. So that will tell me that between a and b it has a probability of p, and 1 minus p v minus b becomes what happens is the Heaviside function becomes 1, h of v minus a becomes 1 when it is above b. So this becomes p plus, and then here it becomes 1 minus p when it is above b. So here what happens is the P and the P get cancelled and you get 1. This is when V is greater than B. And that's what you're getting. You're getting equal to 1. So that's what I'm trying to say. So the PDF would be a delta function. At A, it has a probability of P. And at B, it has a probability of 1 minus P. And these are the only two values it can take. So this is a discrete random variable. So what we have learned is we have taken several different examples. We took a uniform random variable, we took a gamma distribution, a log normal distribution, a Gaussian distribution, and finally a discrete random variable, and saw what the different CDFs and PDFs look like. So if you take the PDF of this discrete random variable, you are taking a derivative of the Heaviside function, and that is why you're getting a delta function. So here it can only take finite number of values. Okay, so that is why the graph also looks like this. And we saw these different distributions where you had CDFs and PDFs. So these were just examples of different random variables that you could have. Different ways you could characterize a random variable. Depending on your application, you could characterize your flow behavior by one of these standard random variables. Although typically we don't tend to characterize velocity by, say, a gamma distribution or a log normal distribution. We do not. These are used a lot in, for example, species transport or chemical reactions where you have to characterize the mixture fraction or the species mass fraction. Sometimes you use some of these distributions there, but not in flow velocities. But it's interesting to know that there are these different random variables that you can characterize it with. Next class, what we are going to do is we are going to look at joint random variables, because we are going to try to delve into velocity, and velocity has multiple components, in which case you would have to consider the joint PDF, the joint probability distribution, and that's what we are going to do in next class. Thank you.